the last few years. He can't come to the meetings anymore, but Jerry still sits in that same row. Sometimes I can look over his shoulder and see his astronomical drawings. So I'm glad that he quit drawing landscapes for a living and started just drawing astronomy objects instead. Here's Jerry Kuchera to tell us about observing and drawing the sun.
Okay.
Thank you for that kind of introduction, John. We're working on a slight technical malfunction at the moment, just with a little mouse here. While we're waiting for that to settle down, I do have a couple handouts that I'd like to give you. This is my opportunity to do so. How many of you are visual observers? Oh, good. Good, okay, so I've got a lot of support here. It's a good feeling to have. I have observation forms I'm going to pass out to each half of the room here. So you can just pass it along and pass it along. One is strictly for solar observing, another one is just a general observing form that I haven't tried the solar observing form because I'm actually a solar observing neophyte. And so I'm just learning about the sun. And I've come here to share with you what I have learned and some of my techniques for sketching at the eyepiece while I'm visually observing the sun. Also, you are guinea pigs because this is an experiment of paper, because this is called Right in the Rain paper. So it's supposedly, even when it gets dewy or moist, it may wrinkle up a bit, but you'll actually be able to run a pencil on it instead of tearing through it, like perhaps some of you have already experienced. This is supposed to hold together and actually hold the graphite as well. So we'll try that and see how it goes. Meanwhile, Ken is working wonders here. Oh, I love you, Ken. Okay. The title of my talk is Here Comes the Sun. And it's a multi-meaning takeoff. Oh, I left this little It's a multi-meaning takeoff of George Harrison's song, a member of the popular group called Beatles.
Here comes
okay.
the sun.
Oh my gosh. Okay.
Here
I have an announcement. You can raise your
chairs.
chairs. I just discovered I can raise my chair, so if you're having trouble, I'll let you know where
Yeah, look at how tall he is now. Oh, okay. 6 feet. I guess be careful how far you raise those stools. Try not to block the other person's head behind you. Okay. I was just saying, the title of my talk is Here Comes the Sun, so some of you already know the song. Maybe you can sing along, but no. In the song, he was singing the words, "Little darling, it's been a long, lonely winter. Here comes the sun, do-do-do-do-do. Here comes the sun," etc., etc. Of course, he did it much better than I did. Something
Where's
like
Jim?
Teresa, who has
We need Jim Shedlowski.
a new idol here. Anyway, the picture seems to be good there. Okay, that happens to be one of my sketches there. That happens to be in color, and it was taken the day before the first flare, I think, of the solar cycle 24, which is what we're coming into. Part of it is in the lower right-hand side there, and this just kind of demonstrates how much detail you can actually see with proper filtering and drawing technique. Now this happens to be in color. We'll talk about just pencil and paper first and then work our way up to a little bit more sophisticated techniques as we go along. But back to the multi-meaning of George Harrison's song, Here Comes the Sun, and the title of the talk. Of course, that means winter is actually coming to an end. March 20th marks the spring equinox, if memory serves me right. And that means, of course, the sun appears to be higher in the sky each day, and that means, of course, more time for observing the sun, which is also a good thing. I grant you that we as astronomers, we also like to stay up late at night, and our night times are short. But hopefully I'll be able to inspire more of you to get out there and, with the proper equipment, safely observe the sun and spend at least those long daylight hours in productivity and enjoyment. It also means, of course, that we are perhaps entering the cycle 24, which is the 24th cycle since 1755, when the methodical recording of sunspot activity began. And either way, we're coming up to a great time to view the sun. So, a quick word about visual observing. Of course, I've got a lot of support here among you, and I appreciate that. And I think you'll agree that one of the great things about visual observing is setup is fast and easy. Here's a picture of me setting up a solar telescope, and it's just got a photographic tripod that I'm putting it on. So I don't have to spend a lot of time setting up. I can just get out there and enjoy it. And another thing, several things I like about visual observing is there's just a organic spontaneity to it. I feel less isolated from nature and the universe. I don't have to sit behind a bank of computers or looking through cameras. Although I'm not disparaging, you astrophotographers. You know who you are. I love you guys. You're great. But I also feel a historical connection with the greats of astronomy, like Galileo, for example. And then there's Angelo Secchi, I believe is his name. He was a Vatican scientist who described many solar structures back in the 1800s, 19th century, that is. And I'll be talking about some of the things that he observed. And astrophotographers like E.E. Bernard, who was a pioneer in the early 20th century in astrophotography, also left a vast archive of sketches and drawings. So, and as Larry, our dearly departed member, Larry Kalinowski, used to tell me, just get out there and observe. And so this is just a great spontaneous way for me, an easy way, I guess, a relaxing way to get out there and enjoy the sun. Okay, so why bother looking at the sun? Well, good question. Well, there's a lot of things exciting about the sun. First of all, it's up all day, and that makes my wife a little happier, because then I don't have to come pouncing in the bed at 3 a.m. and wake her up. She's got to go to work, and kind of makes her cranky sometimes. Second reason, where's the second reason? It's constantly changing, of course. Anyone who has been observing the sun can tell you that there's many phenomena on the solar surface that changes and evolves over days, weeks, days, hours, and as I just witnessed February 23rd, which was just before that solar flare, I saw an eruptive prominence which moved within minutes off the disk of the sun. It was the first time that I've seen it, because I've been starting to observe the sun during solar minimum, and that's exciting in itself, because there's still plenty to see. But this was spectacular, and of course, huge filaments were going across the disk too, which was just great. Okay, the sun goes through an average of 11-year cycles, more or less, waxing and waning, and luckily for me in my talk, I do believe that I'm on the waxing side of solar activity. So I hope after inspiring some of you to actually go out and safely observe the sun, you probably won't be disappointed. I think I can safely predict that. Now when I observe, the time of the telescope is as much an exploration of the imagination as it is the physical presence of observing at the telescope. And when I observe, I usually, in my mind, I start thinking of the big picture and work my way back. Now, as I said, I'm a relative neophyte to solar observing and solar studies, and these are some of the things that I've been reading about the sun. Now, the word on the street about the sun is that it's an earn and burn of churn and funk. Okay. But speaking a little more scientifically, the sun is a gigantic seething sphere of mostly hydrogen gas. Now, from what my reading is, the sun used to be thought of as an average star, but recent research and what I've read about is this premise appears doubtful. There may be many more smaller stars than our sun, and the sun is in the top 10% by mass. So the median size of stars in our own galaxy is probably less than half the mass of the sun. And you can see it there, nicely affixed on the HR diagram. Another thing I learned is that it's a G star. Is that correct, Dave?
Yes,
Yeah, I always thought of it as an M star.
it's about a G2.
My information there is probably from the 70s. So as we know, our sun is of absolute importance to us here on Earth, giving us light and warmth, and indirectly, fossil fuel sources. Well, maybe that's not such a good thing, but it's also of much interest to solar observers. And I'm going to go into that in some detail. I have to make an apology on the outset to the eclipse chasers. I'm not going to be talking about the chromosphere, I'm sorry, the corona of the sun, just in passing. And I want my apologies to Ken
You don't have to apologize.
in particular. I don't know much about it because
Neither did the scientists.
the best time to see it is during an eclipse, okay? And, you know, it is really wild and wacky, but I do have a few things just in passing that I am going to say about. Okay, so the sun is composed of basically 6 layers, or zones, starting with the core, and that's where, of course, the engine that drives the sun is located, the source of nuclear fusion. I've read that the density is about 160 grams per cubic centimeter, which is about 10 times the density of lead, if I'm not mistaken. Now, I would expect such a dense core to be solid, but from what I've read, apparently, because of the fusion reaction is so energetic, the core remains gaseous, although I've been told that it rotates as a solid. So, now the core's temperature is about 15 million degrees. That's pretty hot. That's about 27 million degrees Fahrenheit. In the core, the fusion reactions, as you can see on the right-hand side of the slide, that's there are several steps or several processes that a star can undergo fusion. But this is thought to be the primary one that joins, or that the sun is involved in making most of its energy, and that's basically the proton-to-proton fusion reaction, fusing into deuterium, which then fuses into helium. And that creates a whole lot of energy. And I'll talk about that briefly. But anyway, the gamma rays that are given off are photons of high energy and fine frequency. And the gamma rays get absorbed and re-emitted by many atoms due to the frequent collisions within the core. And as they make their journey outside the sun, as the gamma rays leave their, move outward, their energy starts getting decreased. But thanks to the first law of thermodynamics, which states that energy can neither be created nor destroyed, the number of photons actually increases. So each high energy gamma ray that leaves the core and toward the outer envelopes will eventually become perhaps 1,000 low energy photons. Now, the total output of these reactions is about, those of you who are interested in energy conservation, 386 billion megawatts per second, or just slightly more than our national debt. Now, the solar envelope has a density much less than the core. However, the core contains about 40% of the sun's mass and 10% of the volume, whereas the solar envelope and other 5 remaining layers have 60% of the mass and 90% of the volume. And so they act like a containment vessel, keeping the nuclear fusion from, well, first of all, they keep it hot enough and dense enough for fusion reaction to continue. So the first layer outside the core is called the radiative envelope, as you can see in the schematic drawing here. Its temperature, I think, averages around 7 million degrees Fahrenheit. I don't know what that is centigrade. It's too dang hot for me. But anyway, the solar envelope is cooler, and it's actually more opaque than the core is. It's kind of counterintuitive for me, but that's the way gas works at these high rates of temperature and pressure. Eventually it becomes less efficient for energy to move by radiation, and heat energy starts to build up on the outside of the radiative zone. I want to say radioactive. Must be because of the news.
It's in the air.
Yeah, it's in the air. That brings us to the next layer, which is the convection zone, and that layer is about 200,000 kilometers thick, if I'm not mistaken. So now the energy begins to move by convection in these gigantic cells of circulating gas, several hundred kilometers in diameter. And Ken has read about this in the news, certainly did on Monday. I don't think he had time to do it today, but new research that I've read has confirmed a vast system of plasma currents, and that's shown in the little inset there just to the right of the schematic, kind of the central portion there below the text coronal streamer. You'll see a little black box there, and that's the latest view of the meridional. I think I got that right. Meridional flows, and these are gigantic cells that travel along the sun's surface, and they plunge inward toward the poles and pop up again near the sun's equator. Well, these looping currents play a key role in the 11-year cycle. And in fact, they did computer modeling and trying to predict past activity cycles, and they were actually able to do so. And they think they feel pretty confident that they're able to start plugging in these numbers and using this model to predict future solar minimum and maximum. I think that's pretty exciting to know. Okay, so just to finish, what they feel is happening here. These looping currents actually take the sunspots as they begin to decay and sweep them and their magnetic remains and pull them down into the star about 300,000 kilometers. And that's into the radiative zone. And right about there, you can see in the cutaway, there's some longitudinal flows of strong magnetic fields. Looks like about the temperate zone, north and south of the radiative zone. You can see in that little inset. I hope you can see it. It's pretty small on my screen, but I think you can see it pretty good on your screen. Well, anyway, what they do is they recharge these solar storms, and they eventually pop up to the surface like a cork in water, and a new solar cycle is born. I think that's really, really interesting. Okay, so let's move to the fourth layer, which is called the photosphere. This is starting to get where people like you and me can actually see these types of phenomena and surfaces. I use the term surface loosely. Okay, so the fourth layer is called the photosphere, and it's the apparent visible surface of the sun. It's about 300 kilometers thick. Its temperature is about 6,000 centigrade, so it's cooling off. It's getting more comfortable. The photosphere is composed of convection cells called granules, cells of gas that are approximately 1,000 kilometers in diameter, with hot rising gas in the center and cooling gas falling in narrow spaces between them. Now, of course, at those scales, those spaces are going to be like canyons to you and me. There's some interesting things going on with that, which I'll tell you in a minute here. Anyway, each granule has a lifespan of only about 8 minutes or so, and they result in a continually shifting boiling pattern. You can see in the lower left of the slide there's a little movie that's playing. It's probably blocked by 100 desktops. Well, anyway, it's just showing the boiling. Think of a pot of oatmeal and you pretty much got it. Okay? You can see this through a telescope with a white light filter, that the granules, to me, look like tiny specks of light, giving the sun a kind of a mottled surface. Now in hydrogen alpha light, the granules, to me, have a more 3D appearance, and they make the disk look more like a mottled orange. Almost true to color, too. So the groups of granules make up supergranules, up to 30,000 kilometers in diameter. And I'm guessing those are the ones that, you and I would see through a telescope, the much larger granules, or something in between, perhaps, these supergranules. Anyway, in between those granules, as I was saying, which is essentially, a canyon, a chasm, between the granules, you can actually see something called faculae. And faculae are the views in between those convection cells, and you're essentially looking at the hotter gas that's going to be coming up in the next cell. And those are also things that you can see in white light. Now sunspots are visible in the photosphere as well, and you can see that in the schematic. They're caused by intense magnetic activity, so I think of them as magnetic storms. And as a consequence, they inhibit convection in the hot plasma, which of course conducts electricity and magnetism, and this storm interferes with that convection. And what happens is the temperatures fall, and from about 6,000 degrees to about 3,000 or to 4,200 at most in the sunspot area. So that means they're going to be clearly visible in white light, and I have sometimes trouble seeing sunspots in hydrogen alpha, but I'm waiting for some big ones, so I'm sure I'll be able to see them quite easily then. Oh, another thing, phenomenon that I should mention here is limb darkening. Now the photosphere appears darker at the limb of the sun, and you can see in this illustration why. And basically it's because of the greater absorption of the Earth's atmosphere, the sun's atmosphere, called the chromosphere, and that's which will be the next layer. And the phenomena is called limb darkening, as I mentioned. Okay. Oh, that worked. Okay. The next layer is the chromosphere. I've read recently that the chromosphere is considered to be composed largely of spicules. And let's see if I can bring up the spicules. Okay, the spicules are on the right-hand chart there, a schematic of various size spicules. These were first described by Angelo Secchi, or Secchi, excuse me. I'll get that Italian right someday. And he was the Vatican astronomer that I had mentioned earlier in the talk. And he made a great study of these. Well, anyway, it turns out that these may be very important in the raising of the temperature in the corona. So they're basically dynamic jets of plasma gas, and they are usually about 500 kilometers in diameter or so, but some rise up to 5,000 kilometers or more. And I'll be reading to you some of the latest research on spicules. Now, along the edge of the sun, the larger spicules can actually be seen with proper filtering. I've seen them in hydrogen alpha. I think some people are shaking their head. I have to say I haven't made a great study of them because I'm just a beginner. Okay, so bear with me. The spicules, as I was saying, make up most of the chromosphere. But recently, I was reading fascinating news about the spicules. In 2007, researchers identified a new class of spicules that move much faster and have much shorter lifespans than the traditional spicules, which has speeds between 20 and 40 kilometers per second, which is 12 to 24 miles per second. and lives of 3 to 7 minutes, so they usually don't last long. These type 2 spicules shoot upward at high speeds, often in excess of 100 kilometers per second, which is 60 miles per second, and then they disappear. The rapid disappearance of these jets suggests that the plasma they carry might be very hot, but direct observational evidence of this process was missing. In the January issue of Science, the 2011 issue, the researchers used new observations from the Atmospheric Imaging Assembly on NASA's recently launched Solar Dynamic Observatory and its focal plane package for the Solar Optical Telescope, or SOT, love that name, on the Japanese Hinode satellite. Scott McIntosh, a solar physicist author of the study, says, quote, "Our observations reveal for the first time the one-to-one connection between the plasma that is heated millions of degrees and the spicules that insert this plasma into the corona." Well, I think that's pretty exciting news. Unfortunately, that's all I have to say about the corona. But I do have to talk more about the chromosphere. The chromosphere is where various other transient phenomena occur. And those are prominences, plages, vacuoles, and apparently solar flares. So let's go over those. Let me see if I can look at this. Okay. You can see the prominence there off the limb on the left-hand side of that schematic. Okay, so you can see that prominences are basically eruptions that you observe off the edge or the limb of the sun. And they can be small and spiky, or they can be huge, arcing affairs with feathery-like detail. There's a whole classification system used to classify prominences when you're observing them in HA, hydrogen alpha, which I'll get to a little bit later in the talk. And then there's filaments. Let's see, is a filament? Yes, a filament is in the lower center of the schematic. And those are string-like features on the surface of the sun. Now, I don't know if this is true, but I think they're prominences viewed from the top, top down.
The solar physicists agree with you.
The scientists agree with me?
Yes.
Okay. All right, score one. Been a nervous one. And then there's, after filaments comes plages. Now, there are bright regions in the chromosphere of the sun typically found near sunspots. I've been wondering what the heck that was that I was observing around the sunspots of Carrington. I guess that's what those are. So I learned something. I learned something new. That's great. And then, of course, there's the biggie, the solar flare. Now, the solar flare is, of course, a violent explosion in the sun's atmosphere. Solar flares take place in the solar corona and the chromosphere, heating plasma to tens of millions of degrees. Now, that's in Kelvin, but it's still going to be damn hot if it's centigrade. I'm feeling melty already. Accelerating electrons, protons, and heavier ions to near the speed of light. They produce electromagnetic radiation across the electromagnetic spectrum at all wavelengths, from long-wave radio to gamma rays. Most flares occur in the active regions around sunspots, which I didn't know before. And that's, of course, I guess that makes some sense, because that's where intense magnetic fields are emerging and so forth. So the flare is powered by the sudden release of magnetic energy stored. It goes into the corona and gets released out into the solar system. And these releases, are very fast. I mean, I saw an eruptive prominence. I'm used to looking at these relatively quiescent prominences during solar minimum, and just a couple weeks ago, I was just blown away by the speed at which things changed. And apparently, the same thing would happen if you saw a solar flare. They certainly make for spectacular viewing in hydrogen alpha, and the brighter ones can even be seen in white light, as we shall see. Okay, so now that we've gotten a little familiar with some of the structures in the photosphere and the chromosphere, which you can observe with properly filtered telescopes. Let's cover some of the methods that I've used to record and observe, or I should say observe and record some of these interesting phenomena.
I have a telescope.
I was going to say that till later.
Okay, let's wait till later.
We should also do a survey of the crowd here.
Okay, so before I reveal my equipment, I do want to talk just briefly about safety.
All right.
Safety, right. Looking at the sun is very hazardous, and Dave Bailey was giving me a lecture even during sunrise and sunset. It can be very dangerous to observe, even though you think it's become much more dim. Well, anyway, let's just quickly go through this. Ever look at the sun through any optical device? Okay. Always keep.
That includes just your eye, by the
Yes,
way.
right.
Don't stare at the sun even without an optical device.
I think that's wise advice. Always keep optics capped or with proper filters fastened, and make sure that they don't inadvertently fall off. Gosh, let's see if I can remember. At my first outreach, I brought a white light telescope, and I was all excited. And it was Marty, president of the Solar Observing Group, who advised me to put tape. Don't just rely on the fastening screws. Put tape on there. And you know what? That was great advice, because next thing you know, the winds came up, and some people actually didn't have their filters fall off, but they were jiggling, and they realized they had to refasten them. So, and then of course read all the instructions that come with your equipment, and never ever leave your solar equipment unattended. Don't do it, especially around children. At any time, just don't do it. And then of course, what can I say? Solar observing can also become addictive. So I'm going to cover some of the solar observing techniques that I've been exploring. And one of them is a traditional technique. There's a couple ways of observing in white light, and one of them is white light projection. And this is the traditional way of observing the sun. It's been used since Galileo. And basically, as you can see in the center illustration, a refracting telescope is pointing at the sun. And at some distance from the eyepiece, at the other end of the telescope, where there is a surface that the image of the sun is projected upon. And I found this to be a great way to record and copy the sunspots to scale and properly located on the solar disk. Bright white flares have also been found using this method in white light, and in white light filters too, but the white light projection. In fact, you can see in the lower left-hand corner of the slide, the largest flare ever recorded was in 1859 by Richard Carrington, and he's a fascinating fellow. I think I've got a little bit of blurb on him. Amateur astronomer who demonstrated the existence of solar flares as well as suggesting their electrical influence on Earth and its aurora. You have to remember this is an England. We complain about the clouds in Michigan. I can only assume what an island out, in the Atlantic and North Sea must be like. Anyway, you can see in the right-hand side of the slide, this is his chart over the days and weeks and months of solar sunspot activity and their progression across the solar disk. So this guy was, I don't know how he did it, but he was relentless, and he won many awards. Even though he didn't discover the 11-year solar cycle, his work actually helped lead other scientists to them, and he won awards for his report on the sunspot activity and as it relates to differential rotation of the sun, which he actually determined. And
I got a safety thing about this method.
you mean,
this method is pretty safe as long as you keep people from looking through the eyepiece to try to get a better view. But don't use your most expensive eyepiece because it may melt.
I was just getting to, oh, well, never mind. Okay. No, you're right.
You can't say it enough.
There's
On the other hand, don't use the cheapest because that will melt very quickly, as I've proved.
This is true.
Is that from personal first-hand experience?
At Stargate, yes,
Really?
yes. I got one of those CVS telescopes for $7, and we did solar projection until we saw the eyepiece melt. It was great for about 5 minutes, and then
Okay, so the plastic eyepieces, no good.
no.
It's a different kind of flare.
I also recommend small aperture. So small binoculars are better than big ones.
Oh, well, absolutely. Yeah, don't try this with your Newtonian.
By the way, Jerry, there's one
It does
thing.
work with the Newtonian.
Jerry,
Right.
one thing, actually, the first person to project the sun was Roger Bacon in 1230. But he didn't actually have a telescope, obviously. He built what is known as a camera obscura, and he was able to look both at the eclipses and also the big sun.
Yeah, you know, that is another bona fide observing technique that I have never tried, so I didn't feel worthy of commenting. But that's a great historical perspective. Thank you, Ken.
I did make this pinhole camera thing just with a cardboard box and a paper clip. It's a paper clip to make the hole, and I used the flaps of the opening. So I did it in the side of the box on the short side, so that you get the most distance between that and the other side on the inside, so that you have the biggest projection. In any case, then you look at the opening and you can see the thing. It's very small. So my next design was going to use one of these mailing tubes, this thin thing, because it doesn't have to be very big, just long.
Well, that sounds like an interesting project that I'll have to attempt.
Yeah. And it's my first one took all of it might have been a whole minute to construct, because it's a paperclip making a hole. You're done. Right?
Wow. I was thinking of a small drill, but it sounds even better. Small. I won't have to go hunting for the drill that I've lost. Anyway, so I've used it to, get the scale of sunspots correctly, and I'm going to show that, how I did that in just a moment here. But as, some of you were mentioning, don't use modern complex eyepieces, number one, because the heat inside all that glass can actually melt the adhesive, and that might damage your eyepiece. But what I found is simple eyepiece designs made out of glass. Remember that. The Kellner, I believe it's called, the Huygens, and the Ramsden designs are very basic. In fact, a Kellner design came with one of my solar telescopes, so that's basically what I use. I think that's my most simple eyepiece. And again, never look through the eyepiece of the telescope. Right?
And if you've got a finder, don't use it.
You're right. Don't use it.
Well, the PST comes with just a shadow thing, and that's really the best thing to use.
Right.
Two telescopes.
So if you use a Schmidt-Cassegrain design, is the only safe way then to have an aluminum mylar type filter over the...
Right, a full aperture filter would probably be best for a complex telescope. Now, I have seen, some people actually using Newtonians to observe the sun, and what they've done is they've got a half silver secondary. I really couldn't speak on that. I just prefer, since I have a refractor, I say, use a refractor for goodness sake. That's the.
But for Newtonians or Schmidt-Cassegrains, you wouldn't recommend doing any kind of eyepiece projection, or
No.
because of the heat factor, or...
Not unless it was small. I have actually done it with a 10-inch scope for a very short period of time.
Yeah, I can't comment on it because they're general statements that I have read, don't recommend it. And I have, like I say, went to to the Cloudy Nights Forum and talked to some of the equipment people and solar observing people. And, you know, just in my, you know, I shouldn't say formal, but, you know, just in my basic communication, there have been some people who have said, yeah, I use a Newtonian, but it's a specialized Newtonian that you know, that I don't even silver the secondary, you know, so I can project safely without worry for you know, excessive heat buildup. But I would be concerned about a closed, complex, you know, reflector like a Schmidt-Cassegrain.
Yeah, because he's gonna just keep building up in there.
It could, yeah.
Won't no way to come out really.
Yeah, and maybe there might be someone on the internet who has tried, and you can see the video on YouTube. Yeah,
Really, with a full aperture solar filter, and the club does own an 8-inch.
10-inch.
An 8-inch Schmidt cast with an 8-inch full aperture filter.
I think it's a 10-inch filter. As far as I
Well,
remember.
before we had the bead 10-inch, we had an 8-inch, and we still have the 8-inch. And it does have the full aperture filter, and I use that to good effect. And
right.
you know,
I mean, you can't get a projected image.
No.
but that's because you're cutting down the power at the top, at the front. So the power never really makes it
But
inside.
that's, you know, that's what I would personally recommend for anyone with a you know, complex or compound, you know, reflector. The full aperture, you know, filter, which, well, oddly enough, I'm going to be talking about.
The projection is nice for group viewing, obviously, so you don't have to, you know, put an eye up to an eyepiece, you know. That's why I'm talking about that, because, but if what you got is a Newtonian or Schmidt-Cassegrain, and you want to do a projection, you know, for that reason, well then, saying that you're running the risk of getting
Right.
a lot.
I would think so. I would think so. Now, of course, I use a refractor, and you can see, you know, in the right-hand side of the slide here, next to Galileo's sketch, which is much better than mine, so that's why I put it up there, basically. Anyway, I use a refractor and a simple eyepiece, and you can see what else that I do to cut down on the ambient, you know, glare from just the sky is I put a shallow box, I should say I put the paper and the clipboard in a shallow box that kind of cuts the glare, and then you can see the disk of the sun is starting to shine on the clipboard itself. And what I'm doing is I'm aligning it to fit a template of the solar disk, and it worked quite well. I don't have a problem with it. But you know, I don't know how good this is for group viewing. You know, simply, especially around children, because you know, kids have that natural curiosity, and they don't always listen to instructions thoroughly. Of course, even adults look at it. You see that in traffic, rush hour every day. You know, when I tell them get out of my way, they don't do it. But anyway, this certainly works for you know, for my purposes. But I would be hesitant to have this around kids unless you're really closely supervising, because they want to look through the eyepiece.
Steve, you want to talk about the time you came out to Botsford at all? You did it out at Botsford with the group.
Yeah, I did it out at Botsford. First I showed them the cardboard box, and they got that. That was pretty cool. So these are fifth graders. They're pretty sharp fifth graders, but they're fifth
There were
graders.
about 12 of them, 12 kids.
And this is the pinhole?
So the pinhole with the box.
Oh, okay.
So I made this thing. I tested it. You know, that was like 5 minutes, and then I brought it out to Botsford and I showed it to them, and it worked. I think I did have a white piece of paper in the bottom of the box for where the image goes on. And then I did eyepiece projection with a 60mm spotting scope. The key for safety there, in my opinion, is so this is a spotting scope, it's a refractor. The key for safety is to have the eyepiece so low that the kids couldn't possibly get down there, right? The whole thing was, you know, the eyepiece was probably like 9 inches tops above the ground, right? It was quite clearly focused on a piece of paper taped to a notebook.
Oh, sure.
So that was the second thing, and you know, I basically showed them that you can have a bigger image, and you can start to see more stuff. And then I showed them white light in the 10-inch, I think I had the 10-inch. So white light filter, full aperture filter, and so they got in line and they saw it one at a time through the 10-inch. And since my Dob doesn't track, I had to keep moving the Dob. That's right.
Oh, sure.
And then Bob Berta was there, and he had an H alpha scope, 60 I think millimeter, and so they got to see it in H alpha as well. So we were constantly telling them what the new stuff that they could see. So we had that progression. It was kind of cool.
That's great. Yeah, now the way I've got it set up, you can see I've got it on an equatorial mount, and it's pretty high up. And so it would be at eye level for kids, so
Right.
You can see where I would be hesitant to try this.
Yeah, so I was on with the spotting scope, I was on a photography tripod, and I had the legs all the way in. So it was as short as it could go.
Yeah, well, these legs are, already as short as they could go, and you can still see.
Right. It's still way up there.
I do have you can see I do have a little pillar there above the tripod, so I could probably take that off. But even so, that would still be at eye level for
Right.
a 6-year-old.
So I don't have this 60 millimeter scope anymore. I do have the tripod.
It didn't melt, did it?
No,
Oh, okay.
no. And so if I were to do it now, I probably wouldn't use my 10 by 50 binoculars. I would probably use my 7 by 21 or 8 by 21 binoculars. So smaller is better.
How'd the pinhole camera work?
It was a very small image that you ended up seeing. And that's because my focal length was only, a foot and a half or something like that. So a longer focal length would be better.
Okay, well now I'm going to talk about the white light filter since it's already been broached. I forgot to answer the question about my equipment, but you just happened to see in the previous slide I had a hydrogen alpha telescope and that refractor that was solar projected. And those are the two primary telescopes that I use. Although I'm now using a 6-inch Newtonian, and that's because I have made this large white light filter, as you can see here.
You take photographs also, or is it just?
No, I sketch or record. Okay, so a more modern technique for observing in white light is called white light filters. And basically what that is putting a full aperture filter across the objective or the front of your respective telescope. And you can see in this left-hand side photograph here, there's several. You can see in the inset, this is one way to store them in the little Tupperware containers. Works quite nicely. The two on the left are commercially made. The larger one, as I just mentioned, that was just built by me using instructions from the San Francisco Sidewalk Astronomers website. Great resource. And here I have an exploded view on the right of how it's actually done, and it's actually pretty straightforward. The trickiest thing is to get the right film. Otherwise, you just use strips of cardboard, okay, and I try to use as continuous a strip as possible, and I just formed it around the aperture of the outside of my telescope, and then taped it together, which of course would be later glued. I don't recommend using Gorilla Glue, okay, because that stuff expands, and then you've got air spaces, and you just have a mess. It just oozes everywhere, so don't try it. But anyway, you basically take your film and you cut two circles. As you can see in the middle there's the film, and then the two circles represent the actual cell that holds that film. And then you take that strip of cardboard that you've now glued, that's to the aperture correct size of your telescope, and then you glue the cell of the film to the wall, the vertical wall of that circular aperture fitting cardboard, and voila! Okay, you can see my result. Okay, the reason I put the aluminum foil on there is to cover up the Gorilla Glue oozing, to kind of finish it off, make it look a little bit better, a little less rough, let's put it that way. Okay. I should mention that there are various substrates that are used for white light filters, and some of them, somebody mentioned already, silvered glass. I think they usually put like a thin stainless steel coating on there. I'm not sure what type of metal coating they use. Three Oaks is a company that I recall that actually sells these, or Orion, if you want to say Orion. Well, that's one.
Lake.
And I have one of the Three Oaks type. And Bader is also another company that probably makes some of the best thin film material for white light filters. You could probably buy commercially made ones with Bader film. I haven't used Bader film. The commercial ones that I have use some other products, but I've just recently purchased some of the Bader film to give it a try. And those of you who have used it, think very highly of it. It has exquisite detail. I looked through Bob Burda's white light filter, and I was just on his finder scope, about 50 millimeters, and the detail was it was better than my 3 Oaks filter on my 85 millimeter refractor. So that pretty much tells me it's good stuff. Now for outreach, I've noticed that casual visitors love to see the sun colored yellow. I don't know if anybody else has had that experience. Probably not, because you're using Bader film, which gives you more of a whitish or bluish image. Now, maybe Dave Bailey or somebody else can tell me what is the true color of the sun. I say, well, it must be white, because it's emanating, all the wavelengths that I see. When I look at the sun with my naked eye, sorry, I have done it. As a kid, I didn't listen to my dad, and I stared at the sun for as long as I could, and saw it for 2 days afterwards. But anyway, it looks white to me.
It is white.
So, is it a yellow sun? I mean, you could see.
Yeah, but it's white.
It's always illustrated, or usually illustrated as a yellow sun.
Right.
Well, if you're looking at it from outer space, you would see all the blue light that's been removed.
Filtered out by
Like,
picture.
it's a combination of the blue sky plus the yellow sun that we all know. And that combination, if you're out in space, is pretty much pure white.
Okay. That's good to know. But I have noticed that, I do have a couple white light filters that have a yellowish cast. And I forget the name of the company that sells them.
Teleview.
Who is it?
Teleview. Teleview.
No.
No, Thousand Oaks.
My Orion one.
Well, Thousand Oaks sells the glass.
Right, but they'll also
But
get
there's
your yellow
a
sun.
company that sells the plastic ones, and
Is that just Mylar, or?
it is some sort of, I don't know. I'm not sure.
Gary, we have about 5 minutes left.
Oh, dear.
We want to get to this.
Yeah, let's get to the nitty-gritty. Well, okay, then there's also a Herschel wedge, which I've also used for white light filtering, and that works quite well, but it's more expensive than the full aperture, solar white filters. Okay, so let's get to white light sketching. Hey, we know the precautions. Let's be cool. Well, hey, it's actually pretty easy. The first step is to we're looking at white light, and basically what you can see is the sunspots. So you lightly add some pencil graphite to show the penumbra, which is the outer portion of the sunspot. And then what I do is I take what's called a blending stub, which is a rolled piece of cardboard that's sharpened with a piece of sandpaper. And in fact, it's in that illustration on the left there, in step 1 as I call it. And just blend it kind of gray. The next step is adding the border, if you can see the border, which looks like little streamers, going into the gray part of the penumbra. Well, the solar activity's been so little, I haven't noticed it. And then add the dark umbra, which is the central portion of the sunspot, and then complete the annotation with location, time, magnification. In this case, I actually gave the official designation for those sunspots, and then to determine the sun's actual orientation, I used tilting sun. Some of you probably are aware of that, to just give an orientation of the drawing relative to the sun's location. And then here's the solar prominence that I promised to give you. I hope I don't run out of time to mention. These are some of the prominences that are wonderful to see through hydrogen alpha, which is a light specific to ionized hydrogen. And you can see the chromosphere very well with hydrogen alpha. And the first, let's see, 1, 2, 3, 4, 5 are what's called quiescent prominences, and they have various names. This is called the Zurin class. Okay, so if you go on the internet, you can actually look up this chart. The remaining from F through I are the eruptive type, and you will see these associated oftentimes with solar flares. So when you see these are often in motion, and oftentimes when there's an eruptive prominence or flare about to occur, you'll see these things move very rapidly. I also sketch hydrogen alpha in pencil on white paper, and it's basically the same as in white light, although of course you're going to be seeing more. So you're going to see the prominences, you're going to see the filaments, as well as the plages around the sunspots. Some of the sunspots, may be a little bit faint, but you'll probably be able to see where they're located. So what I do is, in white light, I locate the sunspots first, switch to hydrogen alpha because it's right next to the white light telescope, and off I go. So that's 1 through 4. Step 3, optional step, I should say, to the right of step 4, is scanning your drawing into the computer and changing the colors, the background color, to black, which would more accurately reflect what you actually see in a hydrogen alpha telescope, and then colorize the sun to make it look more like what you would see. And then this is something that I've recently done. I'm using pastel pencils, color pencils, to get the sun's look a little bit more accurate. I think accurate, but what do I know? And basically, it's just adding color a little bit, taking a little bit more time. This particular one took me about a half hour. So I observed for about an hour and a half, and scanning the sun for the prominences and noting them in my mind. Then I took a full disk view of the sun, and I underlaid the circular template drawing with yellow and then a red to make it a lighter color. So then I could easily contrast the filaments and the brighter areas on the disk of the sun more easily, as you can see in step 4 and 5. And then the final result is right there. Okay, so I conclude my talk with some of the references here that I've been able to use to gain more information about observing the sun. Live Science website has some of the latest news on solar work. I haven't really studied the NASA satellites that actually are observing the sun, so I really can't comment too much on those. But the Nearest Star book by Belov and Ashikoff, while it's slightly dated now, it's been a great source of information to get me started in solar observing. And also for those of you who, many of you that I can see here who are visual and would like to start sketching, there's the Cloudy Night Sketching Forum, which I would heartily recommend. Some of the authors, in fact, I have a book here. In fact, if you turn up the lights here, I can show you some of the books.
Ah!
That hurts. Okay, here's a blending stub. Okay, it's just a piece of cardboard rolled up. You can buy that at art store. This is the book that some of the people in the Cloudy Nights Astronomy, Cloudy Nights Sketching Forum actually authored, Astronomical Sketching. Excellent resource.
Cool. Yeah.
Here's the Nearest Star book. Very, very well worth reading. I bought it used very cheaply. Probably get it. I don't think you can get it electrically in ebook form. And then, of course, Astronomy and Sky Telescope have excellent articles. Just recently, here's one about the superstorm, well, I should say the super flare in 1859, and how it may relate to our modern infrastructure. Great article about the sun in general, and as well as super flares and storms in the future. And of course, is the sun an oddball star? Well, probably. That explains a lot of human behavior. Anyway, and then I have a copy of that particular sketch that I just did recently. This was the one where I saw the eruptive prominence here. It was February 23rd. That was the day before the official flare occurred on the 24th. So, there's time, you can come up and take a look at this. That's it for the talk? That's it.
You mentioned about white light and white filter. The hydrogen alpha filter, where is that? Is that at the eyepiece?
No, it's built into my telescope. And it's got a completely different design that, I don't really understand. But I mean,
Well, there's a blocking filter at the front, and then
right,
there's
a-
what's
well,
called
there's
an
a heat-
etalon.
There's a heat rejection filter in
Yes.
the front.
Right, and then there's an etalon that you can tune to
Right.
just see the specific wavelength of light you want to see.
That's
And then-
somewhere in-
Yes, and that's all before the eyepiece. So the eyepiece is a normal unfiltered eyepiece. If you have a hydrogen alpha scope, you don't need any special.
I see.
Well, you never want to use an eyepiece solar filter of any kind.
Thank you.
If Jerry's the Belt of Venus site is almost as convincing as Jerry's talks on getting you started in sketching. It's really beautiful work that he does. So.
Oh, so you've been there?
Yes, I've spent too much time there.
Oh, yeah, that guy is.
I would be better off spending time sketching instead of looking at his, but
I agree.